For our final class, we look at apply the principle of conservation of energy to problems in rigid body kinetics. So, remember when we looked at particles with conservation of energy, we said we can only use it when we have conservative forces that is, they're independent of the path. And so we cannot use conservation of energy when friction is involved. And when we do have applied forces, it's kind of easier to use work and energy even though conservation of energy can be used. So really, what we kind of reserve the method for our problems that involve weights and springs. And so again, it's not really different from work and energy, but when we talk about potential energy, we're talking about stored energy. And so when a weight is above the datum, we can consider that to be stored energy. And when a spring is stretched or compressed, again, it's stored energy. So a weight's potential energy is simply W times Y, where Y is the distance above some datum. And the potential energy of spring is 1 half K delta squared. And so delta, of course, would be measured from the unstretched length of the spring. For kinetic energy, we know that we have this expression that we used when we were talking about work and energy, 1 half mv squared, the translation component, plus 1 half I omega squared, the rotation component. But now we'll show in class that we actually, there is another variation of this, that if point O is a fixed point that the body is rotating about, then we can show that the kinetic energy can also be written as 1 half I omega squared, where the mass moment inertia I is taken about an axis through that fixed point. And of course our equation is that the total energy, total mechanical energy that is, kinetic plus potential, is unchanged. So here's an example problem that we've looked at with work and energy, and also in class we've looked at this same problem with equations of motion. But we want to find the speed after the ramp is rolled down a certain distance, initially at rest, and it rolls without slipping. So initially at rest means the initial kinetic energy is equal to 0. And the only thing doing work here is the weight, which means that the potential energy is just due to the weight. And if we define y as the distance above the final height we're going to reach, then our initial potential energy is just the weight times y. Our usual equation for the kinetic energy, and because of where we set y, we would say the potential energy has gone to 0. So again, we can think of it, it's not different from working energy, but we can really think of the stored energy from having the weight at a height being converted into kinetic energy as it drops over that distance y. And of course, there's only one independent variable here because of the fact that that the velocity of the center of the mass is related to the angular velocity. Now here's one that where we are releasing this beam from rest so it can rotate, and there's a spring that controls that rotation somewhat. And so we're saying that in the initial position shown here, that the spring is unstretched. We let it go, and we want to know after it's rotated a given amount, some angle theta, what's the angular velocity. And so we can, again, we've just got weight in a spring doing work in this case, so we can use conservation of energy. We start from rest, so once again kinetic energy is equal to 0. If we set the datum at the height of the center of mass to begin with here, and the spring is unstretched, then we can say that the potential energy is also equal to 0 here. Now after we rotate through this angle theta, we see that of course we're going to have kinetic energy due to 1 half mv squared for the translation part of the center of mass, plus 1 half Ig times omega squared. But we can also use that form we discussed earlier. Since A is the fixed point that we're rotating about, 1 half I omega squared is the total kinetic energy as long as we're finding the mass moment inertia through an axis through point A. And finally, Have to do a little bit of trigonometry here to figure out the amount that the spring is going to be stretched. But the total potential energy now, since the center of mass is now below the datum, we have minus the weight times h, or minus mgh from the weight. And the spring now is stretched by a value of delta, so 1/2 k delta squared, so stored energy in the spring. And that's it for conservation of energy.